All right, we're back. We're still on page 139. We're just multiplying some things using this newfound knowledge. And so I'm going to dive right in. And so what I'm going to do is I'm going to, so first of all, I could just multiply these. It seems like it'd be kind of ugly because we have radical 3s, radical 2s, whatever. To practice what we're learning, though, I'm going to convert these. So I'm going to say this is Z1, this is Z2. So Z1, I know that if I divide it by 8, I would get the unit circle. So I'm going to say it's 8, and then 1/2 plus radical 3 over 2i. So this will be 8 cis 1/2, so pi over 3. And then Z2, if I divide by 12, will give me a unit circle point. So I'm going to say it's 12 negative root 2 over 2 minus root 2 over 2i, which is 12 cis negative root 2 over 2, negative root 2 over 2 is 5 pi over 4. Okay, so now I want to multiply these. So Z1 times Z2 is going to be 8 times 12, which is 96, and then cis pi over 3 plus 5 pi over 4. And so this is cis. So I mean, if I needed the exact value, I might as well, I'm going to find an exact value, but it's going to be in polar form. If I wanted the rectangular form, I kind of might as well have just like multiplied them out because it would probably be faster to begin with. But I'm like plenty happy to have the polar form because it like tells me how I can plot it and I can visualize it, and like it's less messy, to be honest. So what are we going to use here? 12, I guess. So it's 4 plus 15 is 19 pi over 12. Okay, so let's keep going. So here we go, 3 cis 60. This is perfect. This is already, so this will just be 6, which is 3 times 2, cis 60 plus 90, which is 150. And 150 is 5 pi over 6. I have them all memorized in radians better than I have them in degrees, so I prefer to use that. Negative root 3 over 2 plus 1/2 pi. So I'm just picturing the unit circle point. It's really far to the left and not very high. So that's got to be negative root 3 over 2, 1/2. And then I guess I would do this. Negative 3 root 3 plus 3i. So when they're already in polar form or trig form, it's like that's the way to go. 16 cis. Ooh, 210 plus 330 is 540. Okay, so 540 is coterminal to, I don't know, to what, 180? Or pi? So that's 16 cis pi. We ran into pi before, and I said I thought the easiest thing to do is just kind of like picture it, right? So you're going in this direction, but you're 16 units away, so it should be negative 16. Or you can write it out. So let's see, I'm gonna switch over to the calculator and just see like what can we do? What are our options, right? So on the calculator, one of the things you can do is it doesn't mind how ugly your complex numbers are, right? So we could say Z1 is going to be 2 square root of 3 plus 2 times I, which remembers in the pi key like this. And then Z2, I'll probably just go up, paste. So Z2 is negative 5 square root of 3 over 2, and then 5/2 I. So I can do Z1 times Z2, and I get negative 20, which is what I got. Okay, what if I want to like mess around with cis form? Well, the calculator doesn't know it automatically, but you can program it. So I'm going to type CIS of t. I usually use t for theta. It's just faster. There is theta. It's in the pi key also. Kind of inexplicably, why is there a variable in there? But there is. So you could use that if you want, but it's easier to use t. So this needs to be cosine of t plus I times sine of t. So now it's like set up so it exists. So I thought that I was going to do 4 cis pi over 6 times 5 cis 5 pi over 6. And you can see we still get it. So it's pretty nice. Like cis pi over 6 just gives us what we had. I definitely recommend you do that. Maybe like store it so that you can use it in other documents. I have a separate video on like how to do that if that's something you're interested in. So now I can check like all of them if I need. Oh, series popping up. Let's see. So if I do 8 cis, so I'm just checking at this point. 8 cis pi over 3 times 12 cis 5 pi over 4. And you can see this is easier to type in. Oh, gosh. Oh, and then I got 96 cis. I guess 19 pi over 12 is kind of weird. Here, let's go decimals. So sometimes checking is a pain in the neck. Here. Yes, those are equivalent. So, well, those are equivalent. Yeah, I mean, it's equivalent, but I didn't check like the actual original thing, which I'm not going to do. I'm pretty confident on that. So this one, I'm going to have to convert to radians, but that's not an issue because all year, right? So I get this, which is what we had. And then 8 cis 210 is 7 pi over 6. This is like a good exercise in conversions. Cis 11 pi over 6 to get negative 16, which is what we got. Okay, so let's go back to the notes and take a look at the next problem because it's definitely kind of like the weirdest problem that we've done so far, sort of. And we'll see. Like I think that if you do this on your own, you will definitely get like half of the answers. Well, okay, so I think you'll get all the answers. And I think that in rectangular, there's like one answer basically, because rectangular form A plus BI is unique. Polar form is not unique. There's like a lot of ways to get to a point, and that's going to be an issue. So the first thing I'm going to do is I'm going to say, let's let Z. So we're multiplying Z, a complex number, by another complex number, and we're going to end up with 10 cis 11 pi over 16. But remember, 10 cis 11 pi over 16 is a location, right? It's 11 pi over 6 rotation, move out 10 units. That's a location. There's multiple ways to get there. That's kind of an issue. So I'm going to say Z is R cis theta, right? So then Z times 5 cis 5 pi over 8 is going to be R, so it's 5R times cis theta plus 5 pi over 8. So I just multiplied them, right? Those are our properties. So we multiply the moduli, we add the arguments, and we get this. Now, this is all supposed to be equal to 10 cis 11 pi over 16. So if, so I'm going to say therefore, 5R should equal to 10. What? 5R should equal 10, so R should equal 2. And theta plus 5 pi over 8 should be equal to 11 pi over 16. So theta should be, I don't know, pi over 16? Like 10 pi over 16, 11 pi over, yeah. 11 minus 10 pi over 16. So we get this, but like every angle coterminal of that's going to work. So I'm going to say plus 2 pi n, where n is an element of the integers. So my first answer, and there's going to be another one, my first answer, which I'm actually going to like copy and move over a little bit, is this. I think this is the obvious answer, and I think it definitely works. So Z is going to be 2 cis pi over 16 plus 2 pi n. N is an element of the integers. So what I found was every polar representation of the point that works. Now, the weird thing is, or I think a weird thing, I said that 10 cis 11 pi over 16 is like a location, and there's more than one way to get there. So what I'm going to do is I'm just going to like plot it right now and see if we can make sense of that. Get out of there. Here, and then here. Okay, so 10 cis 11 pi. So 11 pi over 16 is what? It's like it's less than 3 pi over 4. So let's say it's here, right? And then we got to go 10 units. So if I go 10 units, if I go 10 units in this direction, right? That's terrible. That's 10. And then this is 11 pi over 16. Well, can you think of another way of getting there? So like, so someone tells you, you know, close your eyes, rotate 11 pi over 16, walk forward 10 units. This is where you'll end up. There's another way to do it. Someone could tell you to close your eyes, and instead of rotating 11 pi over 16, they could tell you to rotate whatever this is, right? Still on a line, and then walk backwards 10. How weird is that? That'll get you there, right? So if you're facing this direction, but you walk backwards, so negatively, you will also end up there. What I'm gonna do is I'm gonna say that that is, so what are we talking here? Reference angles, right? This is 5 pi over 16. So I'm gonna say that the blue angle is 5 pi over 16 short of 2 pi. 2 pi is 32 pi over 16 minus 5 pi over 16 is 27 pi. Oh, 27 pi over 16. Okay, so another way of writing this, I think, is negative 10 cis 27 pi. And so, like, do we need to do this? I'm not sure of the answer of that. But I think this is a conversation that is definitely worth having, is that you can do this. Both of those put you in the same place. So if someone said rotate 11 pi over 16, move 10 out. If someone else said rotate 27 pi over 16, walk backwards 10, you end up in the same exact place. So it turns out we could multiply this, this, by something else and get this. So that's what I'm going to do right now. So if I let, again, z be r cis theta, this time I would get 5r equals negative 10, and also theta plus 5 pi over 8 equals 27 pi over 16. So pretty different. So here r equals negative 2, and here theta equals, I don't know, 17 pi over 16 plus 2 pi n, where n is an element of the integers. So I think we should check these because, I don't know, this is not really obvious. R is negative 2 cis 17 pi over 16 plus 2 pi n. N is an element of the integers. Okay, so I have two potential answers, and I'm going to check them right now. So let's see. I don't really know how I'm going to check these. I guess multiplying, like, I mean, I might as well, right? So let's start off with what 10 cis 11 pi over 16 is. And let's just confirm, is that the same as negative 10 cis 27 pi over 16? Okay, they're exactly the same. They give the same values. So let's see, if I do, so what did I get? 2 cis pi over 16 times 5 cis 5 pi over 8. Do I get the same value? If I do, then that is a correct answer, and it is. And here you can see I can add 2 pi. Right, that's like checking our plus 2 pi n thing. So far, so good. I'm going to change it up to be negative 2. So this is my second answer, negative 2, and then 17 pi over 16. And this is like a moment of truth. This will either work or it won't. Gives the exact same answer. So either of those work. And that's crazy. Like when we solved trig equations, we saw there were like a lot of solutions, an infinite number of solutions, a lot of different ways of looking at them. Same thing here. So that's maybe more thought than you would have put in. I think everybody would have gotten this answer, right? I think almost no one, because why would you start thinking this way? I don't think a lot of people would think this, but that's why it's important to start thinking that way. There's multiple ways to get to a point, and so you have to consider that. Like if we're trying to find all, so a key thing though is all of these are just polar representations of the same point. So let me go back one more time and then I will cut the video. If I do, let's see, this, right? So the rectangular form is unique. It's this. If I do this, it's going to give me the exact same thing. So they're just different representations of the same point. So rectangular form is unique. There's one location for that point in the like Argand diagram or whatever, right? In the plane, the complex plane. There's one representation of that point. Boom, it's a spot. There's an infinite number of ways of getting to it. And that's a big difference. That's like one of the main differences really between polar and rectangular. Is like rectangular, I tell you to go to point 2, you're at the point 2. In polar, there's a lot of ways that I can tell you to get there. And they're all equally valid. But anyway, I'm gonna cut this here. I'll be back in the next video and we will do more. So hope you're finding these helpful and I'll see you there.